This example problem. We have 1 mole of an ideal gas does 3,000 joules of work on its surroundings as it expands isothermally to a final pressure of 1 atm and a volume of 25 liters. Determine the initial volume and the temperature of the case. So the temperature of this process. So again, we need to identify what type of process we're dealing with. So this is isothermal. With isothermal, we have P initial, V initial equals P final, V final. So I'm just thinking in terms of constant temperature. So that's that one. We have an equation for work and delta E thermal. So these are what I'm writing down. Work is negative nRT, natural log of V final over V initial. And then delta E thermal is 0. So those are the equations that we have in the table that are specific to an isothermal process. Let's go ahead and write down what we know. 1 mole of an ideal gas, 3,000 joules of work on its surroundings. So we would say the work is negative 3,000 joules because the gas is doing work on its surroundings. It's expanding, so energy is leaving the gas. It ends up at a final pressure of 1 atm and a final volume of 25 liters. We want the initial volume and the temperature. Looking at our equations, we have P final, V final. Now, not in SI units, but we can easily get them in SI units. We want V initial, but we don't have P initial. So this top equation's not quite helpful yet. We know our equation for work. We have a V final, V initials in here. So neither of these equations right off the bat gives us anything. So couple other equations. First law of thermodynamics, which in this case, delta E thermal 0. That's always valid. Delta E thermal is NCV delta T. That's always valid, which it's not helpful in this case because there's no change in thermal energy. Something that will be handy here is the ideal gas law. We're dealing with an ideal gas. So we can actually find the temperature here because P final, V final would have to equal nRT final. Now, T's not changing, so T final and T initial are the same thing. So we can solve for temperature using the ideal gas law. We do want SI units, so instead of ATM, I'm going to put in the 101,300 pascals. Instead of liters, I'm going to put in my meters cubed. There's 1,000 liters in a cubic meter. We have 1 mole, R, in terms of SI units. So our moles are going to cancel. The Pascal times meter cubed is a joule. So this temperature is going to end up being in Kelvin. So getting 304.75, so forth. Looks like we're going with 3 sig figs. So 305 Kelvin is the temperature of this gas. And the temperature staying constant. Now volume. The ideal gas law leads us back to a P initial, V initial equals nRT, which essentially is the equation at the top. Because we've been given a value for work, let's use the work equation. We do know the number of moles. R is a constant. We have now found the temperature. So this should be helpful. So negative 3,000 is, N is 1, R is 8.31. Temperature, I'm going to keep a less rounded number in this calculation just to drop down rounding errors. V final, 0.025 meters cubed over V initial. Okay, so we want to get V initial out of the natural log. We can't do that until we have the natural log by itself. So we're going to need to divide the nRT to the other side. So divide this over. I'm getting 1.1846 equals the natural log of 0.025 meters cubed over the initial. Now I can do E to both sides. This becomes E to the 1.1846 is equal to just the final volume over the initial volume. So the initial volume will be this final volume over E to this value. Oops. I'm getting 0.00765. My units are meters cubed because that's what I put my volume, my final volume in with. If I had left that as 25 liters, I would have come up with 7.65 liters. This particular step, the initial volume will have the same units as the final. We did need to convert, though, in using the ideal gas law because the R, the constant we are using, is in terms of SI units.